Welcome to another one of our video lectures in our series Design of Reinforced Concrete Structures. Today is the last video for our chapter 3 in which we are dealing with design of beams in Flexer. And today we will have a tutorial class in which we will see a tutorial regarding the design of flanged beam. In our previous lecture, we considered a numerical problem where we dealt with the analysis part, and today we will see the design part. So the question for design is given on your screen and you can see it right now. We have to design a simply supported flanged beam for the figure that is given alongside here. We have the following data given. First, the depth of the slab or the depth of the T-beam you can say is 100 mm. The total depth of the beam is 750 mm, so that the depth of this web part will be 750 minus 100, that is 650 mm. The cover that is given to our beams is 90 mm. So if we consider that this line here represents the centroid of the group of reinforcement that we will be designing in this problem, then the distance from this line to the top portion is 750 minus 90, which gives us 660 mm. The center to center spacing of beams is 4000 mm. The width of our wave is 350 mm and the imposed load or the live load that is acting on our beam is 5 kN per meter square. Besides, we are also given the effective span of the beam, which is 12 meter, and we have to consider that the concrete grade that we will be using is M20 and the steel is Fe415 grade. So in this design problem, all our dimensions have been given here for the beam that we will be designing. The only thing left for us to design is the amount of reinforcement, and we will design for the reinforcement in this numerical. So to design this flanged beam, first what we have to do is, we know that we are given loads here. We will calculate the factored bending moment that is coming onto our beam, and we will compare that factored bending moment with the moment capacity of our beam. If the moment capacity of our given beam is greater than the factored bending moment, then we will design for an under-reinforced beam, and also we will design a singly reinforced beam here. But if our factored bending moment is greater than the limiting moment capacity of this beam, since we are not allowed to change the dimensions here because the dimensions of our beam are already given, we have to design for a doubly reinforced T-beam. So the first step in our problem will be the computation of factored bending moment. So let us say the step 1 will be computation of factored bending moment. So for that we have to calculate the loads that are acting. You can see that the dead load will be the load of this beam part, this T-beam, which includes both the flange and the wave, and our imposed load will be the UDL that is acting on our beam, that is 5 kN per meter square. So let us consider this flange of our T-beam is the slab portion. So first let us calculate the weight of slab. So weight of slab, first we will calculate per meter square will be given by the thickness of our slab, which is 100 mm, that is the thickness of our flange itself, that is 0.1 meter. Since we are calculating the weight per meter square, we will put both the length and breadth is 1 meter and the unit weight of concrete is 25 kN per meter cube. This we will get is 2.5 kN per meter square. This will be the weight of our slab per meter square. But since we will be calculating all the loads as a uniformly distributed load, we have to convert this to unit weight per meter. So weight of slab per meter is given by this 2.5 into, now what we have to multiply with this 2.5 is, since we are finding the weight of slab per meter of span, we have to multiply this area weight, that is 2.5 kilonewton per meter square, by the width of our beam or width of our slab. And since the center to center spacing of our T-beams, we are only considering this T-beam portion here. Where, okay, we are only considering this T-beam portion here. So the width of this T-beam will be 4 meter. So when you multiply this, you will get the weight of slab is 10 kilonewton per meter. This is one of our dead load. Now another dead load will be the self weight of this wave part, that means this part here. So dead load or DL of wave part of the beam will be given by, again, 25 kilonewton per meter cube, which is the unit weight of concrete, into the width of our wave is 350 mm, that means 0.35 meter, and the depth of this wave is 650 mm, that is 0.65 meter. You will get this to be 5.6875 kilonewton per meter. Again, we have taken the length of this wave portion also is 1 meter, since we are calculating the load in kilonewton per meter. So this will be our dead load of wave part of the beam. And finally, our imposed loads or our live loads is given as 5 kilonewton per meter square. When we multiply it by, again, 4, we will get it as 20 kilonewton per meter. Now our total loads is, add these 1, 2 and 3, you get the total loads is 35.6875 kilonewton per meter. That means this 10, this 5.6875 and this 20. Now after calculating the total load, you can calculate the factored bending moments is 1.5 WL square over 8. 1.5 because we are converting our load here into factored load first. So 1.5 into 35.6875 into the length of our beam is now 12 meter. Our effective span is 12 meters. So 12 square over 8, which comes out to be 963.5625 kilonewton meter. So after calculation of this factored bending moment, what our second step is, our second step involves the computation of axial limiting. We have to determine this axial limiting to know whether our neutral axis is in the wave or flange of the beam. So before computation of axial limiting, let us find the effective width of flange. Let's say that is given by BF, which is the effective width of flange. Remember, when we are calculating the factored bending moment, the effective span of the flange that we are using here is equal to the center to center span, that is 4 meter. So we have to use the actual distance for calculation of load, but for calculation of other factors we have to use this effective width, which is given by, as we discussed during our class, L0 over 6 plus BW plus 6 times dr. L0 means the center to center distance between the points of zero moment, or the center to center distance between the points of contraflexure. And L net is given to us as 12 meter. This is our effective span. So in millimeters you can say 12,000 over 6 plus the width of our wave is 350 mm plus the depth is 6 times df, which is given as 6 into 100. This comes out to be as now 2950 mm. So the effective width of our flange is 2950 mm. That means this BF, which is shown in the figure, is now 2950 mm, and that is less than the center to center span 4000 mm. Now we will be using this BF in further calculations. Let us find Exumax here. Exumax, as we know, this is the limiting depth of neutral axis, is given as 0.48 times D for Fe 415 grade of steel. So this is 0.48 into our effective depth is 660 here, 660, which comes out to be 316.80 mm. So this 316.80 mm is greater than the value of DF, that is 100 mm. That means the neutral axis lies in the wave for Exumax. Remember, this is not the actual depth of neutral axis or not the actual value of Exu for our condition here, but this is the maximum value of Exumax which we may obtain, and for maximum value of Exu, neutral axis lies in the wave, but we have to calculate the actual value of Xu later. Why did we calculate this Exumax here? Because we want to calculate the value of mu limiting. So we know that once we know that the neutral axis lies in the wave, we have to calculate this df by d ratio, which is given as 100 over, now d is 6660, that means 0.15, and this value is less than 0.2, and df by xu, which is given as 100 over 316.8. Here we have used Exumax as xu, and this gives us 0.316, which is less than 0.43. Remember, there were 4 cases for flanged beam, and this df by d value was needed when we know that our beam is balanced, and we need this df by xu value when we know that our beam is under reinforced. So for both cases, the value is less than 0.2 here in df by d, and df by xu is less than 0.43. Hence, if you remember case 2a that we discussed during our classes, we there discussed a formula for finding the value of mu limiting. Since here both cases have come out to be less than the limiting value, we can use the formula that we discussed in case 2a for mu limiting, and that formula is given as mu limiting is 0.36 Exumax over d 1 minus 0.42 Exumax over d FCK BW d square plus 0.45 FCK BF minus BW DF D minus DF by 2. So this is the formula for mu limiting. Now insert all the values here. I'm not going to write the next step, but I'm directly going to write the value of mu limiting. Exumax by d is 0.48, FCK is 20, BW is the breadth of the wave part, which is 350 mm, and D here is 650 mm, that means the effective depth. BF is the width of our flange, effective width that we calculated here 2950, BW is 350 again, DF is 100 mm, and D is 660 mm. So this is not 650, 660. If we insert all the values, you will get the value of MU limiting is 1835.43 kilonewton meter. Now let us compare. Our factored bending moment is 963, which is less than our value of MU limiting. So we can design a under reinforced beam. If this MU limiting value was less than the value of MU, then you have to design a doubly reinforced beam or change the section of the flange beam altogether. But since here we are already given with fixed dimensions, we have to design a doubly reinforced beam. Now once we know that we have to design a doubly reinforced beam, let us go to our third step, in which now we will calculate the actual value of XU. So this is computation of XU. Here we have seen that MU value is less than MU limiting, and this value of MU is almost 50% of MU limiting. That means very much less as compared to the limiting moment values. So what we will assume here is that our neutral axis lies in the flange. Let us assume that our neutral axis lies in the flange. This is our assumption. We will check later whether our assumption is true or not. So when we assume that our neutral axis lies in the flange, we can treat this T-beam as a normal rectangular beam with width BF and the depth or effective depth D. So in that case, when we consider a normal rectangular beam, we can use the value of MU is 0.87 Fy ASTD 1 minus ASTFy over FCKBD. We have used this formula because we assume that the steel in our cross section is allowed to reach the design stress of 0.87 Fy. So all of the factors are known here except the value of AST. So MU we have 963.5625 kilonewton meter, Fy we know, D we know, FCK we know, and B or D also we know. Remember B is BF here. So express this equation in terms of AST, you will get a quadratic equation. Insert all the values, you will get a quadratic equation. AST squared minus 93831.32 AST plus 3794.16711 equals to 0. You will get this quadratic equation in terms of AST. Solve this quadratic equation and take the lesser value, and that will be our required value of AST. So if you solve this equation and take the lesser value, you will get the value of AST to be 4234.72 millimeter square. So once you get the value of AST, check for whether our assumption that neutral axis lies in the flange is correct or not. To do that, we can determine the value of XU using this formula here, 0.87 Fy AST over 0.36 B FCK. If you use this formula and insert all the values, AST now we have, Fy B FCK we know, you will get the value of AST as 71.98 mm, which is less than DF. That means our assumption that neutral axis lies in the flange is correct. So here what we did is that we first assumed the neutral axis lied in the flange. We calculated the value of AST and then we back calculated the value of XU to determine whether our assumption is correct or not. Instead, what you can do is You can find the value of XU first and then find the value of AST. So to determine the value of XU first, what you have to do is you have to use the same formula. I'll just write the formula here. You have to use this mu equals to 0.36 XU over D 1 minus 0.42 XU over D FCK BF D square. You can use this formula first, find the value of XU using this formula, and then use that value of XU to calculate the value of AST also. But first, we did the opposite here. We first assumed that the neutral axis lied in the flange. We calculated the value of AST, and using that AST, we confirmed whether our assumption was correct or not. Finally, once you know the actual value of XU, which is 71.98 mm, in step 4, you can calculate the actual value of AST now. In fact, you have already calculated the value of AST here, 4234.72. Or you can use the formula again. XU by D is given by 0.87 Fy AST divided by 0.36 FCK BFD. From this, you get the value of AST as 4237.41 millimeter square, which is almost equal to the value that we obtained here. So once you calculate the value of AST, check for the minimum and maximum. We know that I'm not going to solve this, you find it yourself. The minimum value of AST is given by 0.85 over Fy into BWD, and the maximum value of AST is given by 0.04 BW capital D. Use the value here and determine AST minimum and AST maximum. The AST value that we got should be greater than this AST minimum but lesser than the AST maximum. So in fact, you will get it greater than this minimum value and lesser than this maximum value. So our AST that we calculated will be correct. Using this AST, calculate the number of bars and the diameter of bars. If we use 6 numbers of 28 dia bars and 2 numbers of 20 dia bars, then you will get the total area of bars used is almost 4322 millimeter square, which is a little bit greater than the AST required. Hence, this design calculation can be accepted and it's okay. Once you get the diameter and the number of bars, you can see for the placement of the bars how you can place them in our actual beams here. So the total bars we have here is 8. What you can do is, if I enlarge this figure here or this figure, whatever you may say, you can in fact put 4 28 dia bars in the bottom line, 2 28 bars in two sides at the upper line, and 220 bars in the middle here in this way. And you have to make sure that the centroid of these bars is at a distance of 90 mm, which is our effective cover here. In this way, you can arrange for the required number of bars. So we have completed the design of this flange beam here. From next lecture onwards, we will start with a new chapter in this design of reinforced concrete lecture series, and that will be related to the design of our beams for shear forces. So we will meet again soon in our next chapter. Till then, stay safe, keep watching the videos on our YouTube channel, and keep subscribing to our channel. Thank you, and see you in next lecture.